At this very moment, a stellar giant, 700 times our sun's width, faces its final days. Betelgeuse consumes material equivalent to our entire solar mass every 6 million years. Yet here's the startling reality most overlook. This crimson behemoth's detonation could occur at any instant, or perhaps 100,000 years hence. And humanity receives merely an 8-minute warning window. Today's exploration ventures into the galactic time bombs lurking in our cosmic neighborhood, stars precipitating liquid metallic rain, binary systems ensnared in terminal gravitational embraces, and gamma-ray beams capable of sterilizing half our world. Should you be prepared to traverse the universe's most perilous regions, engage that like button and subscribe. Steel yourselves. Our journey commences now. The universe's deadliest stars, cosmic time bombs. Within Orion's shoulder region, a celestial body exceeding Jupiter's solar trajectory and magnitude approaches its final chapter. Betelgeuse has sustained combustion for a decade of millions of years, yet currently confronts a terminal challenge. Within its central depths, the atomic forge maintaining this titan's existence begins to waver. Envision an enormous campfire blazing across millions of centuries, its fuel reserves nearly exhausted. Betelgeuse's threat extends beyond its staggering dimensions, though these alone boggle comprehension. Should you position this crimson supergiant where our sun currently sits, it would devour Mercury, Venus, Earth, and Mars entirely. This monster's surface boundary would extend past the asteroid belt. Visualize our complete inner solar system as merely a minuscule sphere contained within this expiring stellar body. The authentic danger originates from the fate awaiting such colossal stars upon fuel depletion. Unlike smaller stellar bodies that transition gently into white dwarfs, Betelgeuse has expanded too massively to expire peacefully. When nuclear processes within its core ultimately cease, gravitational forces will compress the star's center in less than 1 second. The implosion proceeds so swiftly that the core shrinks smaller than Manhattan while maintaining mass surpassing our entire sun. Subsequently comes the recoil. All that compressed substance rebounds and collides with the star's exterior layers at 30,000 meters per second. This impact generates an eruption so tremendous it surpasses entire galaxies in luminosity for months. We designate this phenomenon a supernova. When Betelgeuse undergoes supernova transformation, daytime visibility becomes guaranteed. This situation troubles astronomers during their sleepless nights. This red giant has already begun displaying instability indicators. During 2019, Betelgeuse dimmed dramatically, causing scientists to question whether the eruption had initiated. The star recuperated, yet these alterations inform us the conclusion approaches. The question transcends whether Betelgeuse will detonate. It concerns determining when. The ambiguity derives from stellar chronological scales. When astronomers declare a star will explode imminently, they reference sometime within the subsequent 100,000 years, essentially instantaneous in cosmic terminology. Betelgeuse could detonate during your current reading session, or might postpone until your distant descendants vanish. We simply lack the capacity to predict more accurately. What proves predictable involves the consequences. When Betelgeuse explodes, illumination will arrive at Earth in approximately 600 years. Throughout several months, our nocturnal atmosphere will contain 2 brilliant objects resembling suns. Ancient cave artwork might have documented comparable phenomena from alternative stellar explosions, demonstrating how these cosmic pyrotechnics captivated our ancestors. The eruption will prove spectacular, yet Betelgeuse maintains sufficient distance that lethal radiation won't sterilize our world. We'll obtain premier observation positions for one of the universe's most violent phenomena while remaining completely secure. This renders Betelgeuse distinctive among threatening stars. Most cosmic hazards would eliminate us before we could value their magnificence. This red giant presents something alternative, a countdown toward the supreme fireworks exhibition in human chronicles. Nevertheless, what renders a star genuinely hazardous extends considerably beyond simple magnitude. Our galaxy's most lethal stars all possess one terrifying characteristic: they're sufficiently massive to synthesize iron within their cores. Most individuals assume larger automatically signifies more dangerous, yet stellar physics operates distinctively. A star transforms into a cosmic weapon when it expands beyond 8 times our sun's mass. This boundary determines everything regarding how a star will expire and whether it constitutes a threat to neighboring worlds. Consider stellar mass analogous to a pressure vessel. Modest stars like our Sun can exclusively compress hydrogen and helium together, generating mild fusion processes lasting billions of years. These lightweight stars expire tranquilly, expelling their exterior layers to become magnificent planetary nebulae. They represent the cosmic equivalent of a candle extinguishing. Massive stars function more comparably to nuclear reactors approaching critical failure. The tremendous gravitational force in their cores compels increasingly violent fusion processes. Initially, hydrogen combusts to helium. Subsequently, helium fuses into carbon and oxygen. Temperatures ascend to hundreds of millions of degrees as heavier elements materialize: neon, magnesium, silicon. Each successive element demands more energy for fusion than its predecessor. The star consumes its fuel progressively faster, resembling a vehicle racing downhill with malfunctioning brakes. A star possessing 20 times our sun's mass might combust hydrogen for 10 million years, helium for 1 million years, yet silicon for merely 1 day. The authentic danger commences when the core initiates iron production. Iron nuclei decline to fuse into heavier elements because the process would consume energy rather than generate it. When iron accumulates in a massive star's center, it resembles filling the nuclear furnace with saturated logs. The combustion ceases instantaneously. Without fusion energy pressing outward, gravity compresses the core in under 1 second. The collapse proves so violent that protons and electrons get crushed together into neutrons, discharging more energy than our sun will generate across its complete 10 billion-year existence. This energy tears through the star's exterior layers and propels them into space at 10% light velocity. The eruption generates temperatures of 100 billion degrees, 6,000 times hotter than the sun's core. Under these extreme circumstances, the expiring star forges elements incapable of forming elsewhere in the universe: gold, platinum, uranium. Every heavy atom within your body originated in the terminal seconds of a massive star's existence. Distance establishes whether this stellar death transforms into spectacular or catastrophic. A supernova 25 light-years distant would eliminate Earth's ozone layer and initiate mass extinctions. The identical explosion 100 light-years away furnishes a magnificent illumination display with minimal destruction. The most threatening stars combine massive dimensions with close proximity to Earth. Astronomers have identified dozens of supernova prospects within menacing range of our solar system. These cosmic time bombs could explode tomorrow or in millions of years, and we possess no method to predict precisely when. What renders this even more disturbing involves the sheer magnitude we're addressing. Comprehending precisely how enormous these stellar monsters develop requires transcending everything we comprehend about dimensions. Understanding cosmic scale. Should our sun measure the size of a basketball, The most threatening stars in our galaxy would exceed football stadiums. Scale becomes insignificant when addressing the universe's largest stars. We must construct toward their authentic size progressively, using comparisons comprehensible to human cognition. Commence with something recognizable: Earth. Our world measures approximately 8,000 miles across, appearing tremendous until you recognize that 1 million Earths could occupy our Sun's interior. Our Sun extends 864,000 miles from perimeter to perimeter. Illumination requires 4.5 seconds to traverse its diameter. This renders our Sun a reasonably average star, positioned comfortably in the middle spectrum of stellar dimensions. Envision it as a luminous yellow marble in the cosmic assemblage. Currently, imagine a star 50 times broader than that marble. This introduces us to red supergiants like Betelgeuse, where the term large ceases making sense. Should Betelgeuse substitute our Sun, Earth would orbit inside the star itself, alongside Mars and everything closer than the asteroid belt. The International Space Station would traverse through stellar atmosphere rather than empty space. Red hypergiants propel dimensions into the realm of impossibility. Stars like VY Canis Majoris measure exceeding 1 billion miles across, so enormous that illumination requires 6 hours to travel from one extremity to the other. An aircraft flying at 500 miles hourly would necessitate 2,000 years to circle this monster once. Here's a comparison that might assist grasping the scale. Should Earth constitute a sand grain, our Sun would represent a substantial orange. VY Canis Majoris would constitute a sphere surpassing the Empire State Building in height. The volume differential proves so extreme you could accommodate 7 billion of our suns inside this hypergiant. These massive stars combust so brilliantly they're observable from millions of miles distant. VY Canis Majoris radiates with the capacity of 300,000 suns combined. Should you substitute our Sun with this hypergiant, surface temperature on Earth would instantaneously ascend to 3,000 degrees Fahrenheit, sufficiently hot to liquefy copper. The physics of such enormous stars barely make sense. Their exterior atmospheres remain so loosely retained that stellar winds continuously propel material into space. These expiring giants forfeit mass equivalent to our complete Earth every few million years, yet they're so massive this loss minimally affects them. What proves genuinely mind-bending involves these stellar behemoths living rapidly and expiring young. While our Sun possesses sufficient fuel to combust for 10 billion years total, a hypergiant exhausts itself in merely 3 to 5 million years, less than 1,000th the lifespan of an average star. The largest stars we've discovered remain so unstable they pulse and fluctuate in luminosity over periods of months or years. Their exterior layers expand and contract, resembling the slow respiration of a sleeping giant. Each breath cycle displaces stellar material across distances exceeding Jupiter's orbit. When these cosmic monsters ultimately expire, they don't merely explode, they detonate with the fury of 10 billion hydrogen bombs every second. The 3 phases of stellar death. The death of a massive star unfolds across 3 devastating phases, each more violent than anything humans have ever witnessed. Phase 1 transpires in the terminal seconds before collapse. Deep inside the expiring star's core, iron nuclei accumulate like nuclear ash in a cosmic fireplace. For millions of years, fusion processes have supported the star against its own crushing gravity. Yet iron transforms everything. Rather than releasing energy when it fuses, iron absorbs energy, effectively terminating the nuclear combustion that maintained the star alive. Without energy pressing outward, gravity prevails instantly. The core collapses from Earth's dimensions to 12 miles across in under 1 second. Envision compressing a basketball down to a marble's dimensions in an eye blink, while somehow preserving all original mass. The density becomes so extreme that a teaspoon of core substance would weigh equivalent to Mount Everest. Throughout this collapse, something remarkable transpires. Protons and electrons get compressed together so forcefully they merge into neutrons, discharging floods of ghostly particles designated neutrinos. These neutrinos transport 99% of the explosion's energy, racing through the collapsing star and out into space at nearly light velocity. Phase 2 initiates when the collapsing core impacts the point where even neutrons cannot compress further. This generates a shock wave that rebounds toward the surface at 18,000 miles per second. Consider it resembling dropping a rubber sphere on concrete. The core rebounds with incredible violence, transmitting a wall of energy racing through the star's exterior layers. The shock wave requires several hours to battle its path to the surface, pressing through layers of silicon, oxygen, neon, and hydrogen. As it travels, the wave heats material to temperatures exceeding 5 billion degrees, sufficiently hot to forge elements heavier than iron. Gold, platinum, and uranium all materialize in these terminal moments of stellar death. Phase 3 constitutes the spectacular finale we designate a supernova. When the shock wave breaks through the star's surface, it propels the exterior layers into space at velocities of 6,000 miles per second. The explosion discharges more energy in 10 seconds than our Sun will generate across its complete 10 billion-year lifetime. The illumination from this cosmic detonation can surpass an entire galaxy containing 100 billion stars. Should a supernova transpire 25 light-years from Earth, it would manifest as brilliant as the Sun in our daytime atmosphere. The explosion would remain observable to the naked eye for months, gradually diminishing as the expanding debris cloud cools and disperses. The aftermath generates one of two exotic objects. Stars between 8 and 25 solar masses leave behind neutron stars, city-sized spheres so dense that gravity at their surface proves 200 billion times stronger than Earth's. More massive stars collapse completely into black holes, generating regions where gravity becomes so formidable that even illumination cannot escape. The expanding shock wave doesn't merely generate heavy elements, it propels them into space at incredible velocities, seeding the galaxy with materials essential for planetary formation. A supernova shock wave traverses through space resembling an invisible tsunami, transporting sufficient energy to reshape entire galactic regions. When the explosion initially erupts from the expiring star's surface, it advances at roughly 6,000 miles per second, sufficiently rapid to circle Earth in 45 seconds. This expanding sphere of superheated gas and magnetic fields doesn't decelerate quickly. Even after traversing for thousands of years, supernova remnants maintain velocities of several hundred miles per second. The shock wave presses against the thin gas filling space between stars, generating a destruction bubble that enlarges annually. Consider it resembling a bomb detonating underwater. The blast generates an expanding sphere that displaces water as it enlarges. In space, the supernova remnant displaces cosmic gas and dust, heating it to millions of degrees and accelerating particles to incredible energies. These cosmic shock waves can traverse for hundreds of thousands of years before ultimately exhausting momentum. The Cygnus loop, a supernova remnant observable through telescopes, extends 70 light-years across and continues expanding from an explosion that transpired 20,000 years ago. That constitutes a bubble sufficiently enormous to contain 2,000 solar systems like ours. The destructive capacity of these blast waves depends entirely on distance. Within 30 light-years of a supernova, the shock wave would eliminate planetary atmospheres and sterilize any worlds in its trajectory. Radiation levels would prove thousands of times higher than anything life on Earth could endure. At 50 light-years distant, the effects become more subtle, yet still hazardous. The blast would compromise our ozone layer, permitting deadly ultraviolet illumination from the sun to arrive at Earth's surface. This could initiate mass extinctions by disrupting food chains dependent on plankton and vegetation. Some scientists theorize supernova explosions might have caused several major extinction phenomena in Earth's geological chronicle. Beyond 100 light-years, supernova shock waves become less threatening to life, yet more significant for astronomy. The blast waves compress gas and dust clouds, initiating new star formation. This signifies stellar death directly leads to stellar birth, a cosmic cycle repeating for billions of years. The shock waves also function as giant particle accelerators, propelling protons and atomic nuclei to nearly light velocity. These high-energy particles become cosmic rays filling our galaxy, constantly precipitating down on Earth and other worlds. Gamma-ray bursts, cosmic death rays. The most powerful explosions in the universe discharge lethal radiation beams across billions of light-years, cosmic laser cannons. Gamma-ray bursts represent stellar death elevated to absolute extremes. When the most massive stars collapse, they don't merely explode omnidirectionally, they concentrate tremendous energy into narrow jets piercing through space at 99.9% light velocity. These beams transport more energy than our sun will generate across its entire lifetime, concentrated into streams merely a few degrees wide. Envision a lighthouse beam, yet instead of visible illumination, it discharges gamma rays, the most energetic radiation form in the universe. Gamma rays pack so much energy into each photon, they can split atomic nuclei and generate particle-antiparticle pairs from empty space. When one of these death rays sweeps across a planet, it delivers more radiation than 1 billion nuclear weapons detonating simultaneously. The jets materialize when a massive star collapses into a black hole while rotating rapidly. The rotation concentrates the explosion's energy along the star's magnetic field lines, generating two opposing beams that discharge from the poles. These jets puncture through the expiring star and continue racing through space for thousands of years, gradually spreading as they traverse. Astronomers detect gamma-ray bursts almost daily, yet they're transpiring in distant galaxies billions of light-years away. Even at those incredible distances, the bursts still register on our satellites as brief flashes lasting anywhere from milliseconds to several minutes. The energy output proves so enormous that a typical gamma-ray burst briefly surpasses all the stars in its host galaxy combined. Should a gamma-ray burst transpire in our own galaxy and pointed toward Earth, the consequences would prove catastrophic. The radiation would eliminate our ozone layer in seconds, exposing the surface to deadly solar ultraviolet illumination. The gamma rays would also initiate chemical reactions in our atmosphere, generating nitrogen oxides that would obstruct sunlight and plunge the planet into a frozen winter lasting years. The elimination zone around a gamma-ray burst extends considerably farther than ordinary supernovas. While a regular stellar explosion becomes hazardous within 25 light-years, a gamma-ray burst could sterilize planets up to 6,000 light-years distant if the beam pointed directly at them, roughly 1/4 the distance to our galaxy's center. Fortunately, gamma-ray bursts remain extremely rare, and the lethal beams prove very narrow. The probability of Earth being impacted by one in the subsequent billion years approximates 1 in a million. Even if it transpired, only the hemisphere facing the burst would receive the initial radiation dose, and oceanic life might endure the aftermath. Some scientists speculate gamma-ray bursts might have caused mass extinctions in Earth's past. The Ordovician extinction 450 million years ago eliminated 60% of marine species, possibly attributable to a nearby stellar explosion. The chronology and pattern of deaths correspond with what we'd anticipate from a gamma-ray burst impacting our planet. The kill zone around Earth. Astronomers have charted a sphere of death surrounding our solar system, designating the distance where stellar explosions transform from magnificent to lethal. The elimination zone commences at 25 light-years from Earth. Any supernova closer than this distance would deliver sufficient radiation to initiate mass extinctions on our planet. Consider it a cosmic no-fly zone, where expiring stars constitute a direct threat to life. Within this sphere, a stellar explosion would resemble sitting excessively close to a nuclear bomb. The energy discharge overwhelms any natural protection our planet might possess. At the inner perimeter of this danger zone, a supernova would elevate radiation levels on Earth by thousands of times normal background levels. The gamma rays and X-rays would eliminate our ozone layer within hours, exposing the surface to deadly solar ultraviolet illumination. Oceanic plankton would perish first, followed by vegetation, then the animals dependent on them. The extinction cascade would progress up the food chain until complex life disappeared entirely. Between 25 and 50 light-years distant, stellar explosions become less immediately lethal, yet still hazardous over extended timescales. The radiation would partially compromise our ozone layer, increasing cancer rates and disrupting ecosystems. Some species would survive, yet the biosphere would require millions of years to fully recuperate. This represents a middle zone, where civilization might collapse even if some humans endure. Beyond 100 light-years, supernovas become spectacular illumination displays with minimal biological impact. The radiation arrives weakened by distance, and Earth's magnetic field and atmosphere can manage the excess energy without major ecosystem disruption. These distant explosions furnish magnificent nebulae and valuable heavy elements without threatening life. Current surveys have identified 35 massive stars within the danger zone surrounding Earth. Most of these stellar time bombs sit between 50 and 100 light-years away, close enough to cause concern, yet far enough to avoid immediate catastrophe. The nearest candidate, IK Pegasi, lies 150 light-years away and constitutes no serious threat. What renders this mapping exercise particularly unsettling involves how the elimination zone traverses through space over time. Our solar system orbits the galaxy at 550,000 miles per hour, completing one circuit around the galactic center every 230 million years. Throughout this cosmic journey, we pass through different neighborhoods, sometimes approaching dangerous stars and sometimes distancing from them. 60 million years ago, when dinosaurs roamed Earth, our solar system occupied a different galactic position. Some scientists suspect we might have passed closer to exploding stars during that period, possibly contributing to the mass extinctions that terminated the Mesozoic era. The evidence remains circumstantial, yet the chronology proves suggestive. Looking forward, astronomers predict our solar system will encounter several potentially hazardous stellar regions over the next few hundred million years. These passages through the galaxy's spiral arms increase our probability of experiencing nearby supernovas. The risk never disappears entirely, it merely rises and falls as we journey through the cosmic landscape. Historical supernovas witnessed by humanity. Throughout recorded history, massive stars have exploded sufficiently close to Earth that our ancestors could read by their illumination at midnight. The most famous historical supernova manifested in the year 1054, when Chinese court astronomers noticed a guest star in the constellation Taurus. This cosmic visitor radiated so brilliantly it remained observable during daylight for 23 days. Native American petroglyphs from the identical period might depict this stellar explosion carved into rock faces across the American Southwest. What renders this ancient supernova special involves that we can still observe its remains today. The Crab Nebula, observable through small telescopes, represents the expanding debris cloud from that medieval explosion. At the center sits a pulsar, a neutron star rotating 30 times per second, transmitting lighthouse beams of radiation sweeping across space. Chinese records describe the 1054 supernova as initially brighter than Venus, the third brightest object in our atmosphere after the Sun and Moon. For several months, this stellar explosion furnished sufficient illumination for people to observe their shadows at night. The star gradually diminished over the following year, yet it transformed how humans contemplated the heavens. An even more spectacular explosion illuminated the southern atmosphere in 1604. European and Korean astronomers recorded a supernova in the constellation Ophiuchus that surpassed Jupiter at its peak luminosity. This stellar detonation occurred only 20,000 light-years away, relatively close by galactic standards. The 1604 supernova challenged the prevailing conviction that the heavens were unchanging and perfect. Religious authorities struggled to explain how God's eternal creation could suddenly sprout new stars. The explosion helped fuel the scientific revolution by proving the universe was dynamic and evolving. Earlier historical records suggest even more dramatic stellar explosions. Chinese astronomers in the year 185 documented a supernova that remained observable for 8 months. Roman chronicles from the identical period mention an unusual star that manifested in Centaurus, though their descriptions prove less precise than the Chinese observations. The most intriguing historical supernova might constitute the one recorded in 1006. Multiple civilizations observed this explosion, including astronomers in China, Japan, Korea, and the Islamic world. European monks also noted the brilliant new star, describing it as a sign from heaven that preceded various political upheavals. What proves remarkable about these ancient observations involves their accuracy. When modern astronomers point telescopes at the locations described in historical records, they discover supernova remnants with ages matching the written accounts. The expanding shock waves and glowing debris clouds furnish physical evidence confirming our ancestors' careful observations. These historical supernovas occurred at distances between 6,000 and 20,000 light-years from Earth, far enough to remain safe, yet close enough to generate spectacular displays. The explosions taught early astronomers that stars could originate and expire, laying groundwork for our modern comprehension of stellar evolution. The Crab Nebula, a stellar graveyard. 970 years after Chinese astronomers watched a star explode in broad daylight, the expanding debris cloud still radiates with the fury of stellar death. The Crab Nebula extends 11 light-years across and continues enlarging at 900 miles per second. Consider it a cosmic bubble manufactured from the scattered remains of a star that once outweighed our Sun by 8 times. Every atom of oxygen, carbon, and heavier elements in this ghostly cloud was forged in the terminal moments of stellar collapse. At the heart of this expanding cemetery sits one of the strangest objects in the universe, a neutron star, merely 12 miles wide, yet containing more mass than our entire Sun. This stellar corpse rotates 30 times per second, faster than a helicopter rotor, while generating magnetic fields 1 trillion times stronger than Earth's. The neutron star functions like a cosmic lighthouse, sweeping radiation beams across space with each rotation. When these beams point toward Earth, our radio telescopes detect regular pulses arriving 30 times per second with clockwork precision. Astronomers designate it a pulsar, and its timing proves so accurate it rivals atomic clocks. What renders the Crab pulsar extraordinary involves its youth. Most pulsars are millions of years old and have decelerated significantly from their initial rotation rates. The Crab pulsar is less than 1,000 years old in human terms, so we're observing it in its energetic prime. It pumps out 100,000 times more energy than our Sun, powered entirely by rotational energy left over from the stellar collapse. The pulsar's intense radiation energizes the surrounding nebula, causing it to radiate across the entire electromagnetic spectrum. Radio waves, infrared illumination, visible light, X-rays, and gamma rays all stream from this stellar graveyard. The different wavelengths reveal different physical processes transpiring in the expanding shock wave. Hubble's Space Telescope images display intricate structures within the Crab Nebula that transform from year to year. Knots of gas race outward at thousands of miles per second, while magnetic field lines generate delicate filaments stretching across light years. The nebula resembles a cosmic jellyfish swimming through space, trailing luminous tentacles of superheated gas. The elements scattered by this ancient explosion are already mixing with interstellar gas clouds that will someday form new stars and planets. Every heavy atom in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, was generated in stellar furnaces and distributed by explosions like the one that created the Crab Nebula. Recent studies have revealed the Crab Nebula produces the highest energy gamma rays ever detected from a supernova remnant. These cosmic rays pack more energy than particles in our most powerful accelerators, suggesting the pulsar functions like a natural particle accelerator on a galactic scale. Eta Carinae, the false alarm. In 1843, a star in the southern hemisphere became the second brightest star observable from Earth, convincing astronomers they were witnessing a supernova in progress. Eta Carinae sits 7,500 light-years away in the constellation Carina, rendering it one of the most massive star systems known to exist. The primary star weighs more than 150 times as much as our Sun, so massive it shouldn't be able to exist according to traditional stellar physics. This monster combusts through fuel so quickly it forfeits mass equivalent to our entire Sun every 1,000 years. The 1843 eruption caught astronomers completely off guard. Over the course of several months, Eta Carinae brightened by more than 10,000 times, temporarily surpassing every star in our atmosphere except Sirius. Observers in the southern hemisphere could easily observe it during daylight, and many thought they were witnessing the birth of a new star. What they actually observed was something far stranger, a luminous blue variable experiencing a massive temper tantrum. Instead of exploding completely, Eta Carinea expelled its outer layers in a violent eruption that ejected material weighing 10 times more than our Sun. This stellar outburst generated two distinctive lobes of gas and dust that continue expanding today at 1.5 million miles per hour. The Homunculus Nebula, as astronomers designate this expanding debris cloud, resembles a cosmic hourglass viewed from the side. The structure spans about 1 light-year from end to end and radiates with reflected starlight from the hidden star at its center. Hubble Space Telescope images reveal intricate details within the lobes, including shock waves, magnetic field structures, and regions where fast-moving gas collides with slower material. What renders Eta Carinae particularly fascinating involves that it might represent a preview of how the most massive stars behave before they ultimately explode. The 1843 event discharged as much energy as a typical supernova, yet the star survived by shedding mass instead of collapsing completely. This suggests hypermassive stars might experience several false alarms before their final detonation. Modern observations reveal Eta Carinae is actually a binary system consisting of two massive stars orbiting each other every 5.5 years. The primary star weighs about 150 solar masses, while its companion tips the scales at 30 to 80 solar masses. When these two monsters orbit close together, their stellar winds collide and generate spectacular pyrotechnics observable across the electromagnetic spectrum. The system continues displaying instability signs. Astronomers have detected smaller eruptions occurring roughly every few decades, suggesting the star remains on the verge of another major outburst. Some models predict Eta Carinae will explode as a supernova within the next million years, practically tomorrow in astronomical terminology. Should Eta Carinae explode, it will remain observable during daylight from Earth and might even cast shadows at night. The explosion could also produce a gamma-ray burst, though the probability of the lethal beam pointing toward Earth remains extremely small. Luminous blue variables, stellar imposters. Across our galaxy, the most massive stars play a deadly game of cosmic peekaboo, disappearing behind clouds of their own ejected material before blazing back to life. Luminous blue variables represent the most unstable and unpredictable stars in the universe. These stellar giants weigh between 50 and 200 times more than our Sun, rendering them so massive they exist right at the edge of what's physically possible for a star. Like vehicles driving excessively fast on a winding mountain road, they're constantly on the verge of losing control. The instability originates from their incredible energy output. A typical luminous blue variable produces more than 1 million times as much illumination as our Sun, powered by nuclear reactions so violent they literally attempt to explode the star apart. The radiation pressure from this intense fusion presses outward with such force it nearly overcomes the star's own gravity. This generates a stellar balancing act that can tip either direction without warning. Sometimes the star prevails in the tug-of-war and pulls its outer layers back inward. Other times, radiation pressure dominates and the star violently ejects massive amounts of material into space. These eruptions can cause the star to appear brightening by thousands of times in merely months or years. The most famous example constitutes P Cygni, a star that initially manifested to European astronomers in 1600 when it suddenly brightened to third magnitude, easily observable to the naked eye. The star diminished and disappeared, then reappeared several more times over the following decades, earning it the nickname Nova Cygni, or New Star in Cygnus. What observers were actually observing was a massive star undergoing violent outbursts, each one ejecting material equivalent to several times our Sun's mass. The star would temporarily conceal behind its own ejected debris, then radiate through the expanding shell as the material dispersed. Modern telescopes reveal P Cygni sits surrounded by complex nebular structures generated by centuries of these explosive episodes. Luminous blue variables confront a fundamental problem. They're excessively massive to maintain stable nuclear combustion. The core temperatures and pressures needed to support such enormous stars initiate runaway fusion reactions that periodically destabilize the entire stellar structure. It resembles attempting to maintain a controlled explosion in a bomb factory where the workers keep adding more dynamite. These stars also rotate incredibly rapidly, spinning at velocities approaching the breakup limit where centrifugal force would tear them apart. The rapid rotation generates complex magnetic fields that can suddenly discharge stored energy in massive stellar flares. Some eruptions might result from magnetic reconnection events, similar to solar flares, yet scaled up by factors of millions. The unpredictable nature of luminous blue variables renders them particularly hazardous neighbors. Unlike regular supernovas that announce themselves through predictable stellar evolution, these cosmic tricksters can explode without warning during what appears a routine eruption. The star might seem to experience another false alarm until the collapse suddenly accelerates past the point of no return. Wolf-Rayet stars, naked stellar engines. Deep in our galaxy, combust stars so incredibly hot their surface temperatures reach 200,000 degrees Fahrenheit, sufficiently hot to vaporize any known material instantly. Wolf-Rayet stars represent the terminal stage of evolution for the most massive stars in the universe. These stellar furnaces have already combusted through their hydrogen fuel and stripped away their outer layers, exposing the nuclear reactor at their core directly to space. What remains constitutes essentially a naked stellar engine operating at maximum capacity with no protective shell. The surface temperatures of these stellar monsters exceed 50,000 degrees Celsius, 10 times hotter than our Sun's surface. At these extreme temperatures, the stars radiate brilliant blue-white and pump out enormous amounts of ultraviolet radiation. A single Wolf-Rayet star produces more energy than 100,000 suns combined, compressed into an object only slightly larger than Earth's orbit. This incredible heat generates stellar winds so powerful they expel away material at velocities up to 3,000 miles per second. Consider it resembling a cosmic hairdryer turned up to maximum power. The star literally expels itself apart with its own radiation. These stellar winds prove so intense they can strip away material weighing as much as our entire Sun every 10,000 years. The winds generate spectacular nebulae around Wolf-Rayet stars as the ejected material collides with surrounding gas clouds. The Ring Nebula in Lyra formed this way, though its central Wolf-Rayet star has since evolved into a white dwarf. Current Wolf-Rayet systems display similar bubble-like structures expanding at hundreds of miles per second. What renders these stars particularly fascinating involves their chemical composition. The nuclear reactions in their cores have progressed far beyond simple hydrogen combustion. Wolf-Rayet stars are actively fusing helium, carbon, oxygen, and even heavier elements in their interiors. The stellar winds transport these fusion products directly into space, enriching nearby gas clouds with elements essential for planetary formation. The extreme conditions inside Wolf-Rayet stars generate some of the rarest elements in the universe. These stellar furnaces can produce significant amounts of fluorine, neon, and other elements that materialize only under very specific temperature and pressure conditions. When the star ultimately explodes, it will scatter these exotic materials throughout the galaxy. Most Wolf-Rayet stars exist in binary systems, orbiting around companion stars that assist stripping away their outer layers. The gravitational interaction between the two stars accelerates the mass loss process, exposing the Wolf-Rayet core even faster. Some of these binary systems display periodic brightening as material flows from the Wolf-Rayet star onto its companion. The lifespan of a Wolf-Rayet star proves incredibly short by astronomical standards. These stellar blowtorches combust so intensely they exhaust their remaining fuel in merely hundreds of thousands of years. Since they've already shed most of their mass through stellar winds, Wolf-Rayet stars typically explode as relatively small supernovas or collapse directly into black holes. Binary star death spirals. When two massive stars orbit each other sufficiently closely, they initiate a gravitational dance that can only terminate in mutual destruction. Binary star systems containing two giants generate some of the most violent and spectacular phenomena in the universe. As these stellar partners orbit each other, they gradually forfeit energy through gravitational waves, ripples in space-time itself that transport momentum away from the system. This energy loss causes the orbit to decay, bringing the stars closer together in an accelerating death spiral. Consider it resembling two figure skaters holding hands and rotating faster as they pull closer together, except these cosmic dancers weigh millions of times more than our Sun, and their final embrace discharges more energy than entire galaxies produce. The process can require millions of years to unfold, yet the terminal moments transpire with devastating velocity. During the early stages of orbital decay, the stars initiate tidally distorting each other. Their immense gravitational fields stretch and compress their stellar companions, generating bulges that point toward each other like cosmic teardrops. Material from the outer layers starts flowing between the stars, forming streams of superheated gas spiraling inward at tremendous velocities. As the orbit continues contracting, the stellar winds from both stars initiate interacting and colliding. These wind collision zones generate shock waves that heat gas to millions of degrees and accelerate particles to nearly light velocity. The resulting radiation can be detected across the electromagnetic spectrum, from radio waves to gamma rays. The most dramatic binary evolution transpires when one star explodes as a supernova while its companion survives. The explosion expels roughly half the system's total mass in seconds, suddenly reducing the gravitational binding that maintained the orbit together. The surviving star gets ejected from the system at velocities that can exceed 600 miles per second, sufficiently rapid to escape our galaxy entirely. These runaway stars race through space, trailing shock waves and bow shocks as they plow through interstellar gas. Astronomers have discovered dozens of these stellar refugees, their high velocities and unusual chemical compositions furnishing evidence of their violent origins. Some runaway stars display clear signs of having been contaminated by material from their exploded companions. Even more exotic scenarios unfold when both stars in a binary system prove sufficiently massive to explode. The chronology of these double supernovas depends on the initial mass ratio and orbital characteristics. Should both stars explode within a few million years of each other, the second explosion occurs in a cavity generated by the first supernova's shock wave. Some binary systems manage to avoid immediate destruction, yet still confront inevitable doom. When both stars evolve into compact objects like neutron stars or black holes, they continue spiraling inward while emitting gravitational waves. The terminal moments of these mergers generate some of the most energetic phenomena in the universe, briefly surpassing entire galaxy clusters. The collision of two neutron stars produces gravitational waves sufficiently strong to detect on Earth, alongside gamma-ray bursts and the production of heavy elements like gold and platinum. Type 1a supernovas, standard cosmic candles. In distant galaxies, expiring white dwarf stars explode with such precise energy that astronomers utilize them as cosmic lighthouses to chart the expansion of the universe itself. Type 1a supernovas initiate with white dwarf stars, the dense remnants left behind when sun-like stars exhaust their nuclear fuel. These stellar corpses pack roughly the mass of our Sun into a sphere the dimensions of Earth, generating gravitational fields so intense that a teaspoon of white dwarf material would weigh as much as a pickup truck. Most white dwarfs cool slowly over billions of years, diminishing into cosmic embers that ultimately become invisible. However, white dwarfs in binary systems can experience a very different fate. Should a white dwarf orbit sufficiently close to a normal star, its intense gravity initiates stealing material from its companion, gradually increasing the white dwarf's mass. This cosmic theft continues for millions of years as hydrogen-rich gas spirals down onto the white dwarf's surface. The stolen material accumulates in a thin shell around the stellar remnant, compressed and heated by the intense gravitational field. Eventually, temperatures in this accreted layer reach the point where hydrogen fusion ignites explosively. The thermonuclear explosion doesn't merely combust the surface material, it initiates a runaway chain reaction that detonates the entire white dwarf. Consider it resembling a cosmic hand grenade, where the pin gets pulled when the star reaches precisely 1.4 times the mass of our Sun. This critical mass, known as the Chandrasekhar limit, represents the maximum weight a white dwarf can support before collapsing. When the explosion occurs, it completely destroys the white dwarf, converting roughly half its mass directly into energy through nuclear fusion. The blast discharges as much energy as our Sun will produce over its entire 10 billion-year lifetime, all within the span of seconds. The explosion propels the star's remains into space at velocities of 20,000 miles per second. What renders Type 1a supernovas so valuable to astronomy involves their remarkable consistency. Since every explosion involves a white dwarf reaching the identical critical mass, they all discharge nearly identical amounts of energy. This renders them standard candles, cosmic light bulbs with known luminosity that astronomers can utilize to measure distances across the universe. By comparing how brilliant these supernovas appear from Earth to their actual energy output, astronomers can calculate precisely how far away their host galaxies are located. This technique has revealed that the universe's expansion actually accelerates, driven by a mysterious force designated dark energy that constitutes 70% of all existence. Type 1a supernovas also function as cosmic factories for iron peak elements. The thermonuclear explosion generates perfect conditions for synthesizing iron, nickel, cobalt, and other metals essential for rocky planet formation. A single Type 1a supernova produces more iron than our Sun contains total mass. Core collapse, the final second. When a massive star ultimately exhausts nuclear fuel, the collapse from a sphere larger than Earth's orbit to a city-sized neutron star transpires faster than a human heartbeat. The terminal moments initiate when iron accumulates in the star's core, like ash in a cosmic fireplace. For 8 million years, nuclear fusion has supported this stellar giant against its own crushing gravity. Yet iron transforms everything. Unlike lighter elements, Iron nuclei absorb energy when they fuse instead of discharging it, effectively terminating the nuclear combustion that maintained the star alive. Without fusion energy pressing outward, gravity prevails instantly and completely. The stellar core, initially about Earth's dimensions, initiates collapsing under its own weight. What transpires next unfolds so rapidly that describing it in human terminology becomes almost impossible. In the first half-second, the core contracts from 8,000 miles across to merely 50 miles, while maintaining all its original mass. The density becomes so extreme that atomic nuclei get compressed together like marbles in a compacting trash receptacle. Electrons and protons are compressed so forcefully they merge into neutrons, discharging floods of ghostly particles designated neutrinos. By the 1-second mark, the core has compressed to merely 12 miles across, smaller than Manhattan, while weighing more than our entire sun. At this point, even neutrons cannot be compressed closer together. The core has reached nuclear density, where matter behaves according to exotic physics we can barely comprehend. The collapse terminates abruptly when neutrons initiate resisting further compression. Consider it resembling a rubber sphere being compressed to its limit. It suddenly rebounds with tremendous violence. The core rebounds, transmitting a shock wave racing outward through the star's outer layers at 18,000 miles per second. This shock wave confronts a monumental challenge. It must battle its path through thousands of miles of stellar material, pressing against the incredible gravitational field of the collapsing star. For several hours, the battle remains uncertain. The shock wave weakens as it travels outward, and many computer simulations display it stalling before reaching the star's surface. What preserves the explosion involves the neutrinos. During the core collapse, these nearly massless particles transport away 99% of the explosion's energy. Most neutrinos escape without interacting with anything, yet in the incredibly dense conditions near the stellar core, a tiny fraction get absorbed by the stalled shock wave. This small energy boost proves sufficient to revive the explosion. Between 8 and 15 seconds after the initial collapse, the shock wave ultimately breaks through the star's surface. The outer layers, containing thousands of Earth masses of material, get propelled into space at 10% light velocity. The star has become a supernova, observable from millions of light-years away. Throughout these terminal 15 seconds, temperatures in the shockwave exceed 100 billion degrees. These extreme conditions forge elements heavier than iron that cannot materialize anywhere else in the universe. Gold, platinum, uranium, every heavy atom in existence was generated in the terminal moments of a massive star's existence. Neutron stars, the crushed heart. The stellar core that survives this cosmic violence becomes one of the strangest objects in the universe. The compressed heart of an exploded star generates an object so dense that a sugar cube of its material would weigh 6 billion tons on Earth. Neutron stars represent matter compressed to the absolute limit of physical possibility. When a massive star's core collapses during a supernova, protons and electrons get compressed together so violently they merge into neutrons, the identical particles found in atomic nuclei. The result constitutes essentially a giant atomic nucleus 12 miles across, containing more mass than our entire sun. To comprehend this incredible density, envision compressing Mount Everest down to a sand grain's dimensions while preserving all the original rock. A neutron star packs so much matter into such a small space that gravity at its surface reaches 200 billion times stronger than Earth's. Should you somehow stand on a neutron star, you would weigh as much as Mount Everest. The surface of a neutron star proves stranger than science fiction. The crust consists of atomic nuclei arranged in crystalline structures stronger than diamond, while the interior contains forms of matter that cannot exist anywhere else in the universe. Some regions might contain nuclear pasta, matter organized into shapes resembling spaghetti, lasagna, and gnocchi at the subatomic level. Most neutron stars rotate rapidly, revolving dozens or even hundreds of times per second. This rotation originates from conservation of angular momentum, resembling a figure skater rotating faster when pulling their arms inward. When a star with slow rotation collapses to neutron star dimensions, the rotation rate increases dramatically. Neutron stars also possess magnetic fields trillions of times stronger than Earth's. These intense magnetic fields channel radiation into narrow beams that sweep across space like lighthouse beams. When one of these beams points toward Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. We designate these objects pulsars, and their timing proves so precise they rival atomic clocks. The Crab pulsar, formed from the supernova Chinese astronomers observed in 1054, rotates 30 times per second and pulses with clockwork regularity. Its magnetic field proves so formidable it could erase every credit card on Earth from halfway to the moon. The pulsar functions like a cosmic dynamo, converting rotational energy into radiation and slowly decelerating over millions of years. Some neutron stars experience starquakes, sudden shifts in their crusts that discharge more energy than all earthquakes in human history combined. These phenomena can alter the star's rotation rate measurably and generate glitches in the pulsar timing that astronomers can detect from thousands of light years away. Black holes, the ultimate collapse. When the most massive stars expire, they collapse so completely they puncture holes in the fabric of space-time itself, generating regions where the normal laws of physics break down. Black holes materialize when stellar cores exceed roughly 3 times the mass of our Sun, beyond the point where even neutrons cannot resist gravitational collapse. At this critical threshold, nothing in the known universe can halt the inward fall. The stellar core continues contracting past the neutron star stage, past the dimensions of atoms, past the realm where our current physics can describe what transpires next. The collapse generates a gravitational field so intense that space and time become severely warped. Consider space-time as a stretched rubber sheet and a black hole as a bowling ball generating such a deep depression that anything rolling nearby falls in permanently. The boundary around this cosmic trap constitutes the event horizon, the point of no return where escape becomes impossible. What renders black holes genuinely bizarre involves how they affect time itself. According to Einstein's theory of relativity, intense gravitational fields decelerate time relative to outside observers. Near a black hole's event horizon, time dilation becomes so extreme that seconds stretch into hours or years when viewed from a safe distance. Should you somehow watch someone fall into a black hole, you would observe them decelerate as they approach the event horizon, their image growing redder and dimmer until they faded from view. From the falling person's perspective, they would cross the event horizon in normal time and continue toward the center, though tidal forces would stretch them into a long, thin shape resembling spaghetti. The center of a black hole contains what physicists designate a singularity, a point where density becomes infinite and the curvature of space-time becomes so extreme that our current comprehension of physics breaks down completely. We simply don't understand what transpires at the singularity because our mathematical tools fail under such extreme conditions. Stellar mass black holes range from roughly 3 to 100 times the mass of our Sun, depending on the original star's dimensions. The event horizon of a typical 10 solar mass black hole spans about 37 miles across, sufficiently small to accommodate inside most major cities. Despite their reputation, black holes don't actually absorb material from large distances. Their gravitational influence at long range proves no stronger than the original star. Black holes can only be detected indirectly through their effects on nearby matter. When material falls toward a black hole, it forms an accretion disk that heats up to millions of degrees and radiates brilliantly across the electromagnetic spectrum. These feeding black holes become some of the brightest objects in the universe, observable from billions of light-years away, triggering new star formation. The violent death of massive stars initiates a cosmic chain reaction that compresses nearby gas clouds and ignites the formation of new stellar generations. When a supernova explosion tears through space, it doesn't merely scatter the remains of the expired star, it functions like a cosmic bulldozer, pressing against the thin gas filling the space between stars. This interstellar medium contains the raw materials for future star formation: hydrogen, helium, and heavy elements forged in previous stellar generations. The expanding supernova shockwave compresses these gas clouds to densities hundreds of times higher than normal. Consider it resembling compressing a sponge filled with cosmic gas. The compression forces material together until gravity can assume control and continue the collapse. Regions that were previously too diffuse to form stars suddenly become sufficiently dense to ignite nuclear fusion. This process generates spectacular stellar nurseries observable throughout our galaxy. The Orion Nebula, one of the most magnificent objects in our nocturnal atmosphere, materialized when massive stars in the region exploded millions of years ago. The shock waves from these ancient supernovas compressed surrounding gas clouds, initiating the formation of hundreds of new stars that continue illuminating the nebula today. The chain reaction doesn't terminate with a single generation. The most massive stars born in these compressed regions will themselves explode as supernovas within a few million years, generating new shock waves that initiate additional rounds of star formation. This generates expanding bubbles of stellar birth that can propagate across hundreds of light years. Our own solar system likely materialized this way. Isotopic evidence in meteorites suggests a nearby supernova explosion compressed the gas cloud that ultimately became our Sun and planets. Heavy elements like aluminum-26, which decays rapidly, manifest in primitive meteorites at concentrations that could only result from a recent supernova enriching our local environment. The shockwave compression process proves remarkably efficient at generating massive stars. While normal star formation tends to produce mostly lightweight stars like our Sun, supernova-triggered star birth generates a higher proportion of massive stars that will ultimately explode themselves. This leads to clusters of massive stars that combust brilliantly but briefly, generating spectacular stellar associations. The cosmic recycling of heavy elements. Every atom in your body heavier than hydrogen was generated in the nuclear furnace of an expiring star and scattered across the galaxy by cosmic explosions. The process of stellar nucleosynthesis initiates in the cores of massive stars, where temperatures reach hundreds of millions of degrees, sufficiently hot to compel atomic nuclei to fuse together despite their natural electrical repulsion. This cosmic alchemy transforms simple hydrogen and helium into progressively heavier elements through a series of nuclear combustion stages. In the star's core, hydrogen nuclei fuse to form helium, discharging tremendous amounts of energy that maintain the star radiating. When the hydrogen exhausts, helium nuclei initiate fusing into carbon and oxygen. As the star ages, successive combustion stages generate neon, magnesium, silicon, and ultimately iron, each new fusion process demanding higher temperatures and pressures than the last. Consider a massive star as a cosmic onion with different nuclear reactions occurring in concentric shells. The hottest center combusts silicon into iron, while outer layers continue combusting lighter elements. This generates a complex internal structure where different regions of the star produce different elements simultaneously. The authentic treasure trove of heavy elements materializes during the terminal supernova explosion. In the 15 seconds of core collapse and rebound, temperatures ascend to over 100 billion degrees, conditions so extreme they enable fusion reactions impossible under normal stellar conditions. These moments of cosmic violence forge elements heavier than iron through rapid neutron capture. Gold materializes when iron nuclei rapidly absorb dozens of neutrons before having time to decay, accumulating atomic masses through successive captures. Platinum, silver, and other precious metals follow similar pathways. The entire periodic table of elements heavier than iron, roughly half of all known elements, can only be generated during supernova explosions or neutron star mergers. The explosion propels these newly forged elements into space at thousands of miles per second, seeding nearby gas clouds with materials essential for planetary formation. Over billions of years, this stellar debris becomes incorporated into new generations of stars and their planetary systems. The calcium in your bones was forged in the core of a red giant star. The iron in your blood materialized during a supernova explosion. The oxygen you breathe was generated when a massive star fused helium nuclei together. Even golden jewelry underwent nuclear transformation in the terminal moments of stellar collapse. The iron peak, where fusion stops. Iron represents the terminus for stellar fusion, the element where nuclear physics demands that even the most massive stars must cease combusting and confront their inevitable death. The reason lies in the fundamental nature of atomic nuclei and the forces binding them together. When lighter elements fuse, hydrogen combining into helium or carbon combusting to form oxygen, the resulting nuclei prove more tightly bound than their components. This discharges energy that powers the star and generates the outward pressure needed to resist gravitational collapse. Iron 56 sits at the peak of nuclear binding energy, signifying it possesses the most stable nucleus possible. Consider it resembling a valley in the energy landscape of atomic nuclei. You can roll down toward iron from either direction, yet you cannot climb back up without adding energy from outside. This renders iron the cosmic terminus for fusion reactions. When a massive star's core initiates producing iron, it resembles filling a nuclear furnace with material that refuses to combust. Instead of discharging energy through fusion, iron nuclei would necessitate absorbing energy to fuse into heavier elements. The nuclear combustion that supported the star for millions of years suddenly extinguishes, leaving only gravity to determine what transpires next. The iron core enlarges rapidly as outer layers continue combusting lighter elements and adding to the iron accumulation. Silicon combustion, the terminal fusion stage before iron production, can convert the star's entire core to iron in merely a few days. Once the iron mass exceeds about 1.5 times our Sun's mass, the core becomes unstable and collapse becomes inevitable. What renders this process so dramatic involves the velocity at which it unfolds. A star can combust hydrogen for millions of years, helium for hundreds of thousands of years, and carbon for thousands of years. Yet once iron starts accumulating in significant quantities, the star possesses perhaps hours or days before collapse initiates. Red hypergiants at the edge of possibility. In the depths of our galaxy exist stars so enormous that should one substitute our Sun, its surface would extend beyond Jupiter's orbit. Red hypergiants represent the absolute upper limit of stellar dimensions, expanding so large they challenge our comprehension of how stars can exist at all. These cosmic monsters measure over 1 billion miles across, distances so vast that illumination requires several hours to traverse from one extremity to the other. An aircraft flying at cruising velocity would necessitate over 2 million years to circle one of these giants. VY Canis Majoris, one of the largest known stars, spans roughly 1,500 times our Sun's diameter. Should you hollow out this hypergiant, you would necessitate over 3 million Sun-sized stars to occupy the volume. What permits these stars to expand so incredibly large involves their relatively cool surface temperature. While smaller stars combust hot and brilliant, red hypergiants possess surface temperatures of merely 3,000 degrees Celsius, sufficiently cool that their outer layers expand to enormous distances. Consider it resembling a balloon being inflated. The identical amount of material spreads out over a considerably larger volume. The physics of such enormous stars barely make sense. Their outer atmospheres remain so loosely bound that stellar material constantly escapes into space through powerful stellar winds. These hypergiants forfeit mass equivalent to our entire Earth every few thousand years, yet they're so massive this material loss hardly affects them. Red hypergiants combust through their nuclear fuel at prodigious rates, consuming mass equivalent to our entire Sun every million years. This incredible fuel consumption signifies they can only exist for a few million years before exhausting their energy reserves. In cosmic terminology, they resemble cosmic firecrackers, combusting brilliantly but briefly before exploding. When red hypergiants ultimately explode, they generate some of the most powerful supernovas known. The sheer amount of material involved signifies these explosions can surpass entire galaxies for months. The blast waves from hypergiant supernovas can initiate star formation across vast regions of space. The Chandrasekhar limit, a fundamental boundary. One specific number, 1.4 solar masses, determines whether an expiring star explodes as a supernova or collapses directly into a black hole without any pyrotechnics. This critical mass limit, discovered by Indian astrophysicist Subramanian Chandrasekhar in 1930, represents the maximum weight that electron degeneracy pressure can support. When stellar remnants exceed this threshold, quantum mechanics itself cannot prevent gravitational collapse from continuing indefinitely. To comprehend why this limit exists, envision electrons as cosmic construction workers attempting to support a collapsing building. In normal matter, electrons orbit atomic nuclei at comfortable distances, yet under extreme pressure, electrons get compressed closer and closer to the nucleus until quantum mechanics declares they cannot be compressed any further. This quantum resistance generates degeneracy pressure, a fundamental force that possesses nothing to do with temperature or chemical reactions. Even at absolute zero temperature, electrons would still resist further compression because of quantum mechanical principles. This renders electron degeneracy pressure incredibly reliable as a source of stellar support. White dwarf stars depend entirely on electron degeneracy pressure to maintain their structure. These stellar remnants pack roughly the mass of our Sun into a sphere Earth's dimensions, generating densities where a teaspoon of material weighs as much as an automobile. The Chandrasekhar limit represents the precise point where gravity becomes stronger than quantum mechanics. When a white dwarf accumulates mass beyond 1.4 solar masses, usually by stealing material from a companion star, electron degeneracy pressure can no longer support the stellar remnant against its own weight. What transpires next depends on how quickly the white dwarf reaches this critical mass. Should material accumulate slowly over millions of years, the white dwarf gradually approaches the limit and then explodes as a Type 1a supernova. The explosion completely destroys the white dwarf, leaving nothing behind. Predicting stellar explosions. Astronomers have created a cosmic watch list of massive stars that could explode within the next million years, though predicting precisely when remains one of astronomy's greatest challenges. The fundamental problem involves that stellar timescales dwarf human experience. When astronomers declare a star will explode soon, they reference sometime within the next 100,000 to 1 million years, practically tomorrow in cosmic terminology, yet thousands of human generations in the future. Even our most sophisticated computer models cannot narrow down the timing more precisely than this. What we can predict with confidence involves which stars are approaching their terminal stages. Stars more than 8 times our Sun's mass will definitely explode as supernovas, while less massive stars will expire peacefully as white dwarfs. Astronomers utilize several techniques to assess stellar danger levels. Spectroscopic analysis reveals what elements exist in a star's atmosphere, indicating how much nuclear combustion has occurred in the core. Stars displaying heavy nitrogen and helium at their surface have likely initiated combusting through their hydrogen reserves and may be approaching the red giant phase. Stellar variability furnishes another significant clue. Stars nearing the terminus of their existence often become unstable, displaying periodic brightness alterations as their outer layers pulsate or get ejected in violent eruptions. The red supergiant Betelgeuse has displayed increasing variability over the past few decades, suggesting it may be approaching its terminal explosive phase. Binary star systems offer additional predictive capacity. When two massive stars orbit each other, astronomers can calculate their orbital evolution and predict when stellar collisions or mass transfer phenomena might initiate explosions. The most promising candidates for future explosions include Wolf-Rayet stars, which have already shed their outer hydrogen layers and are combusting helium in their cores. These stellar blowtorches represent the terminal evolutionary stage before core collapse, rendering them prime supernova candidates within the next few 100,000 years. Red supergiants like Betelgeuse and Antares also rank high on the danger list. These massive stars have exhausted their core hydrogen and are combusting heavier elements in concentric shells around their centers. Computer models suggest they possess at most a few million years of fuel remaining before iron production initiates collapse. The Global Monitoring Network. Across the world, automated telescopes sweep the atmosphere every night, watching for the telltale signs that massive stars are about to explode and unleash their cosmic fury. This global surveillance network operates resembling an early warning system for stellar catastrophes. Robotic telescopes in Chile, Hawaii, Australia, and other dark sky locations continuously photograph the identical regions of space, comparing new images to reference pictures taken days, weeks, or months earlier. Computer algorithms analyze these comparisons, searching for stars that have suddenly manifested or dramatically altered brightness. When a potential supernova is detected, alerts transmit instantly to observatories worldwide. Within hours, the largest telescopes on Earth and in space can be pointed toward the explosion to capture its spectrum and monitor its evolution. This rapid response capability has revolutionized supernova science, permitting astronomers to study stellar explosions from their initial moment. The monitoring systems have become so sensitive they can detect supernovas in galaxies billions of light-years away, explosions so distant their illumination has been traversing toward Earth since before our solar system materialized. Modern surveys discover several hundred supernovas each year, compared to merely a handful detected annually before automated searches initiated. Closer to home, special attention concentrates on monitoring individual massive stars for instability signs. Betelgeuse receives almost daily observations through multiple wavelengths of illumination, tracking alterations in its luminosity, surface temperature, and dimensions. Similar monitoring programs watch other supernova candidates like Eta Carinae, Rigel, and Deneb. The most sophisticated monitoring involves interferometry, combining illumination from multiple telescopes to generate images sufficiently detailed to resolve stellar surfaces. These observations reveal hotspots, cool regions, and mass ejection phenomena on individual stars, furnishing unprecedented views of stellar evolution in action. Space-based telescopes add crucial capabilities to this monitoring network. The Hubble Space Telescope can track subtle alterations in stellar spectra that indicate shifts in surface composition or temperature. X-ray satellites detect high-energy emissions from stellar winds and circumstellar material that might signal approaching instability. Gravitational wave detectors represent the newest addition to the cosmic monitoring system. When massive stars collapse into black holes or neutron stars, they generate ripples in space-time itself that traverse at light velocity. These gravitational waves transport information about stellar collapse that cannot be obtained through any other method. The monitoring data feeds into increasingly sophisticated computer models that attempt to predict stellar behavior. These simulations incorporate stellar physics, nuclear reactions, magnetic fields, and rotation to model how massive stars evolve toward explosion. Machine learning algorithms currently scan monitoring data for patterns that human astronomers might overlook. These artificial intelligence systems can identify subtle correlations between stellar properties and explosion chronology, potentially leading to better prediction capabilities. The ultimate goal of this cosmic surveillance network involves protecting Earth from stellar threats while maximizing scientific knowledge gained from stellar explosions. Every monitored star brings us closer to comprehending how the universe's most massive stars exist, expire, and influence the cosmic environment around them. As we continue observing these stellar time bombs, we remain both thrilled by their magnificence and sobered by their awesome destructive capacity.